very exciting presentation by Dr. Roger Espasa, who started his career with a doctorate degree at the Università Politecnica di Catalunya, UPC, and then since then he has a long history of working in research in the public sector, but also very much in industry, including contributing to the alpha architecture, working with top computer company, and now he's running his own company since 2016. He has SemiDynamics, of which he is the primary founder, and that recently, as you will learn, has been specializing on the development of this new open architecture RISC-V, based processor. So you will certainly learn a lot of very exciting things is what is happening on that field. So without any further ado, Roger, the floor is yours. You can go.
Thank you very much. First of all, thank you very much for the invitation. Let me share. Let me know that you're seeing the title. As I was saying, thank you very much for the opportunity to speak at this school. I see a lot of people connected, and feel free to ask questions and stop me. Otherwise, this feels a little bit dry in this new virtual pandemic world. So today I'll talk a little bit about the RISC-V course we've been developing and the support they have for vector instructions following the RISC-V vector spec. It's we'll go through the microarchitecture of Avispado a little bit and how we can connect to external vector units. Let's click here. What's going on? Okay, so as Fabrizio kindly said already, we are an IP provider. We're headquartered in Barcelona, Spain. We were founded in 2016, and we've done a little bit of everything. A project that we've done that has recently hit the news, if you're interested, we did all the architectural work and RISC-V cores and vector unit for a US company called Esperanto. They recently presented their SoC at Hot Chip. So if you fancy to know about what we did a couple of years, that's what we were doing. And right now, our main activities, we're a proud participant in the European Processor Initiative. In fact, we work with BSC, we work with Extol, Forth, Fraunhofer, Unizagreb, many European partners together to develop the vision of a European accelerator. So we're very, very proud to be in that initiative. So having said that, let me talk a little bit about our high bandwidth RISC-V IP course. We have two cores, one we call Avispado 220. It's a 2-wide in-order core. Supports something I'll describe, which we call gazillion misses. It's a commercial name. And it has RISC-V vector support, and I'll describe what that means. We also have another product, which is called Atrevido 220. It's a 2-wide out of order. So the fundamental difference between these two products is that one's in order, the other one's out of order. It also supports the idea of gazillion misses and also has RISC-V vector support. Today, we'll focus on Avispado, and I'm happy to answer questions about the other one, but I think I have enough slides to bore you on Avispado. We won't have time to get to Atrevido. So why do we call them high bandwidth cores? What do we mean when we say a high bandwidth core? What does that exactly mean? And really, we mean a core with lots of outstanding memory requests. That's what we mean by that, right? So we've used this commercial term. We call it a core with gazillion misses. So we can trademark the name. And what we really let me go through that in a little bit of detail, right? This is a gathering sparse data. If you can read the code on the left, which is stylized C, you have some while loop. You load from an array of A using an index. So A of index of I, that's a problem because that's an irregular access. Then you load some data B of I, then you compute, and then you store C of I, right? If you can read the stylized assembly code on the right, which tries to be RISC-V in spirit, what would you do? How would you compile the code on the left to new code, right? You would load the index of I into some register, right? You would then load that register as an address. So you would do an indirect load, if you, so to speak, second line, load X5 into X6. You would load the actual data from the array A that you want to load. Then you would load B of I, then you would do some computation between this A of I and B of I, and then you would store the result, right? And that's, perfectly common for many of you here interested in HPC. That's extremely common in HPC applications, but it's also common in AI applications, very specifically in recommendation systems. This comes up very, very often. How do most cores execute this? And I have a little animation here at the bottom, and that animation actually, sorry, let me make this small. Oops, this is bothering me. Sorry. This horizontal line represents time. And what will a typical computer, a typical core do on the loop on the right? Well, you'll do some loads, right? You'll make a request. This arrow R1 is a request for possibly the load for index of I, right? So you'll make that request. You cannot make the next request, and you want to make the load B of I request. So you could do two requests. If you have a very a very aggressive core, what tends to happen is you'll do a couple of those, and then depending on your core, maybe you can loop around in a speculative way and start the loads for the next iteration. So maybe you can do a couple more. In my animation, I put 8 requests to the memory system. This would represent, in this particular loop, a computer capable of going around this loop 4 times. That's not a lot, so let's count instructions. 1, 2, 3, 4, 5, 6 instructions. 6 times 4 is 24. So, you can go around about, you need a reorder buffer or a graduation list, whatever name you want to use, of about 24 instructions. And many of the high-end Intel processors, AMD, ARM processors, all of these guys can do that, unroll the loop dynamically, and get to these loads and do it. However, and I'm sorry, that's a very long intro. However, what's key here is that after 8 requests, and we'll see in a second a chart showing how many requests, most machines will just stop. They'll say, okay, I've done 8 cache misses or 8 misses in my local core. I've made my 8 requests. I've done a great job. I'm very happy. I'm going to sleep until when? I'm going to sleep until the first request corresponding to the first instruction of the first iteration comes back, right? So you are now going to wait L cycles, so many, many cycles, right? Typical latency is more than 100 clocks until what? Until the data for request 1 comes back, right? And this is, we'll show that in this timeline with D1, meaning the data for request 1 finally came back after a long while, right? And yes, indeed, then you will be able to make your 9th request. So now you could go around the loop one more time and make 9 requests. And this is great. But it's not that great, right? You've made 8 requests in how long? Well, let's say these requests were super good and they came out in 8 clocks, and then you waited 100 clocks. So you've done 8 requests in 108 cycles. That's your bandwidth, 8 divided by 108. Actually, we should multiply the request by the data size, but you get the point. So that's your bandwidth, right? What we want to do, right, what we want to do with our technology and what we've changed the core extensively to support is the idea that we don't want to do 8 requests and stop, right? What we want to do is to be able to actually continue all the way to 128 requests, right? So if needed, unroll this loop as many times as necessary. And we'll discuss in a second that this works really well when you have vector instructions, right? So what you unroll this, and so this way, when the data comes back, notice more or less what happened here. We made 128 requests, and we more or less have hidden the 100 cycles of wait time. So this wait time, I've put something here to not say it's 0, right? But it's very, very close to 0. So by the time the first request comes, you're already making the request 129. That's one of the key features of the course we've been designing in the context of the European Processor Initiative, right? So we want, these cores are meant to be for accelerators, are meant to be for applications that have a lot of sparsity, are meant to be for applications that have a lot of, that require a lot of data, like in HPC. And therefore, we expect those cores to actually not fit in the cache. And therefore, we expect those cores, really, I should say the applications are not going to fit in the core cache. And therefore, those applications are really going to need a lot of bandwidth. And this actually supports making those bandwidth requests, right? Okay. So let's compare with other cores. In this chart, I'm showing you the issue width of cores. So, you know, our cores are 2 wide, so they will be here on the number 2. And there's a plenty of cores in the market with, you know, that issue lots of instructions. And here I'm plotting the outstanding misses as reported in the public literature, right? So let's start at the beginning with the Power 9, a very, very powerful 6 wide out of order core supporting four threads by IBM. And these guys can do 16 requests to the memory system. So it's not bad, it's 16. Another relatively recent core, as time goes by, I should update my slides, but Ice Lake, which is fairly recent from Intel, is a 5 wide core from Intel and can make 12 requests to the memory system, right? When they're missing their L1 cache. The ARM A76, we found also information, is a 4 wide machine supporting 20 outstanding cache misses. And then in the RISC-V world, the information is not so available. We know, for example, the Boom designed by Berkeley, which is a 4 wide out of order, can do 10 outstanding misses. And then Sci-Fi announced a core called the U8. Recently, they re-announced it as the P550. And we think, we're not sure how many outstanding misses they have, but we think they're going to be below 10. So we placed it here as a 3 wide issue and around 10. We're not exactly sure. Syntacore also offers RISC-V cores with 2, but also again below 10. And at the low end, we have the Andes cores, also RISC-V, doing very few outstanding misses. Comparing with this data, the thing I'm talking to you, the Avispado core, can support 64 and more outstanding misses. And the one we're not going to describe today, the out of order one, we can extend that all the way to 128 cache misses. So, I hope this chart helps you see more or less where we're positioning these scores. These scores are not, if your data fits in cache, then by all means by Intel or by ARM, right? If your data is not going to fit in your L1 cache, which we think that's common for AI applications and for HPC applications, then we think our cores are a great choice. What else? So what is this good for? I think I already covered that. This is good for machine learning. Things like TensorFlow, PyTorch naturally exhibit this need to make lots of requests. In particular, within machine learning, it's especially good for what's called recommendation systems. If you've followed recent presentations and publications by Facebook, Amazon, and even Google, they're all explaining how a lot of their AI workloads are about recommendation. Recommendation system, to pick an easy example, you all know these companies that offer video services, Netflix and you all know that they make you recommendations. They say, oh, if you watch this movie, we think you're going to like the next movie. Well, that is a recommendation system. Likewise, the ads that you get presented when you connect to Instagram or to Facebook or to your Gmail are also the result of a machine learning computation of a recommendation system. So I hopefully that wasn't too much of a repeat for this audience, but those recommendation systems have very, very sparse matrices, something they call the embeddings, right? And the embeddings are very large and very sparse, or to be more precise, the embeddings are very large and they're accessed in a sparse way, right? So that's another thing where that's good for. What else? Key value stores. We have not, we don't have a particular example, but if you look at the way memcache and things that are just a key and a value, they exhibit also a lot of sparseness, right? So these kind of applications should also run well on this course, right? And obviously, this being an HPC school, I couldn't leave the slide without mentioning that in HPC, sparse data is actually something very, very natural. So we think it goes without saying that this is going to be good for HPC. Now, this is the application view. Let me also tell you that if you were a system designer, you're building your chip, why would we recommend our core? You're going to say, of course, because it's yours, sure. But I mean, what would be the scenarios where that would make sense? For example, a scenario where you, in the past, you had a core, maybe a DDR system, and some limited SRAM or cache, right? What do people do these days? Well, people create a system like this, maybe for IoT, maybe embedded, and what they end up spending a lot of time is putting DMAs to get the data from the DDR into the core. Those DMAs end up causing a lot of pain in the software team in that company, because now, instead of the core just making requests, the poor software team needs to actually do buffer copy from the DDR into the SRAM, buffer copy out, and synchronize the copies, and then there are bugs in the synchronization and stuff like that. Right? So we tell people that, hey, if you're in that situation, even if you have a single core, this ability to make lots of requests to memory system is going to be very useful, because it will allow you to make your software team, your software actually simpler by just having the core make all the requests it needs and fully using the DDR, right? On the other extreme of the scale, if you were somebody building a gigantic, SoC with 6 HBM2 stacks or HBM3 or whatever is the latest, and lots of compute in the middle, again, you have a tremendous amount of bandwidth available, so you want cores capable of using that bandwidth. And again, we would say that, hey, our cores are actually good for that. And it goes without saying, but we'll talk about it on vector units. If you have a vector unit, that's going to make big demands on the memory system by itself. That's a natural ability of a vector unit. It does a vector load and makes lots of requests to memory. That's a fantastic attribute of vector instructions, right? Well, if the vector unit makes lots of requests and you don't have a core capable of supporting those memory requests, then you'd be in trouble, right? You put a vector unit and you can't really use it, right? So that's, again, a place where our technology, we think, is great. Okay, let's go into the core details. Fabrizio, if you're, how long do we have for this talk? Sorry, do we have a full hour, less? I can't remember.
Yeah, you have a total of 1 hour, including question and answer.
Okay, good, excellent. Fantastic. So let's go a little bit into, since this is a school, I did try to put more details on the pipeline, and I'll be happy to answer questions as we go. So that's what the Avispado core looks like from a pipeline, from a microarchitecture point of view, and we'll go through this left to right little by little. So let's see. Obviously, the first pipeline stage is the PC. We select the PC, and with that, we index the iCache. The iCache is 16 kilobytes 4-way, and when you see this star next to something, it means that's customizable. So we, being someone that sells IP, if a customer comes and says, well, 16 kilobyte too much, I can live with 2 kilobytes, we'll happily change it for the customer, right? The ITLB, that's important. We do support, it's a full MMU design, so we fully support virtual memory, and we fully support booting Linux on this core. And we support both the SV48 virtual memory model and the SV39. So SV48 is less common in that it's a very wide virtual address, but SV39 is pretty popular. So both work. And of course, in this first stage, we do have a branch predictor. It's a tag-based branch predictor, has a BTB, of course, and a return address tag. So it's fairly decent in branch prediction capabilities. Okay, so after these first two stages, the iCache, if everything goes well, of course, and you guys that are listening know about how branches always cause trouble, but if everything goes well, we get 64 bytes out of the iCache, so 512 bits, a full cache line, and we queue it into this little decoupling queue. If there's an iCache miss, this queue is responsible, it's not really a queue, it's responsible to making a request to the outside world, getting the data back, putting in the iCache, and resuming fetching, right? The queue will deliver 8 bytes to the decoder, and the decoder will look at the 8 bytes in RISC-V. As you know, oops, that arrow is wrong. That arrow should go to the decoder, apologies. The decoder will produce a maximum of 2 instructions. If the instructions are 4 byte wide, then that's it. We've consumed the 8 bytes. If we're lucky and we do support the compressed instructions, the instructions may be only 2 bytes wide. Then out of these 8 bytes, you've only consumed 4, and you still have 4 bytes more that you can deliver in the next clock. The key point here is this is an in-order machine. It delivers 2 instructions in order. There's we call this the memory issue queue, the general issue queue, and the vector floating point issue queue. We call them queues for historical reasons. They're really, this is an in-order machine, so really this is like almost one flip-flop. There's actually 2 flip-flops for latency and timing reasons, but it's really, it acts as a a single entry thing. So let's go to the top pipeline, which is probably the most interesting. If we decode a load instruction, it will go, or store, load and store, it will go into the memory issue queue. By the way, the other comment here that says we decode the vector spec, and we'll describe later how if we see a vector load, the vector load will also go to the top, to this memory issue queue to be processed. So let's take a normal load. A load will go through this stage, the vector AGU that I'll describe later when we talk about vectors. Then we'll go through the DTLB. Again, we support SV48, SV39, so full MMU support, Linux capable. From there, we look into the L1 cache. The L1 cache is 32 kilobyte 8-way. Again, customizable. We can reduce ways. We can reduce total size up to the customer choice. And then we go through the aligned network after reading the data. By the way, the core does full hardware support for unaligned. So if you do a load of 8 bytes and you give me an address that's not a multiple of 8, no problem. Sorry, no problem is if you know the RISC-V spec, you know that it's allowed to trap on such accesses. They're called unaligned accesses. We don't trap. We solve it in hardware. It's going to take you a couple clocks to complete the load, but we will solve it for you in hardware. In fact, in many cases, we do an unaligned at full speed. So unless the unaligned crosses a cache line, we do it at full speed. What else do we have up here? If you miss in the Dcache, I hope my mouse moves and you guys see my mouse moving because I keep moving the mouse and hopefully that's going through. So if we miss the Dcache, we go through this gazillion unit, which is the one that's capable of handling many requests. And then we go out to the coherent interface. And in fact, we can support here, depending on the customer, AXI, which would be non-coherent, of course, ACE or CHI. So that's up to the customer of what they want, right? Okay, the load makes all the requests, and when the data comes back, we put it in the cache and return the data to the rest of the pipeline. Moving forward, let's go back to the decoder. If we decode an integer instruction, it will go into the general issue queue. It will go into the integer unit, return the data, and complete, right? And finally, if we get a vector or a floating point instruction, it goes to the VFIQ, vector floating point issue queue. And from there, it will go into the FP unit. I made the FP unit bigger because it's a 5-cycle floating point unit, whereas the integer is, most operations in the integer unit are single cycle, but that's fairly standard. And we'll describe later the vector unit details. We obviously have breakpoint support and external debug over JTAG and the debug module. So if you put that in your SoC, then you can, obviously, you get access to the debug port of the core. I'll pause here a second. Maybe there are questions here, or if someone wants to ask a question. Check time. Okay, 25 minutes. Good. Okay, we'll keep going now. Okay, let's talk a little bit about the RISC-V vector instructions, right?
Before you continue, Roger, there is one question on the chat.
Okay.
By Adrian.
Oh, is it possible to get access or to get an Avispado device? Yes and no. You can get today a bit stream, so you could try this on an FPGA. That's available immediately. You may have seen that EPI has reported that we taped out the first device, and we are now waiting for the packaging house to return packaged EPI devices containing Avispado cores. So as soon as that is available, I mean, it's not commercially available, but if you have a particular interest, get in touch with us, and we'll be happy to see if we could get you a device, or if there's a good use for it. You know, we'll discuss with the API partners and see if we can get you one. Okay. Okay, let's move on to the vector part, which we said we would describe. So let's see, a little bit of history. Oh, okay, maybe I forgot to say one base. I always forget that. I assume it. Sorry, I forgot to mention these letters down here, RISC-V 64 GCV. This is a 64-bit microarchitecture. So you know that RISC-V supports a 64-bit profile and a 32-bit profile. This is the 64-bit one. The G means general, means it supports all the instructions required for Linux. The C means it supports compress, which we discussed. And the V here means it means that we support the vector extensions. Let's describe that. As you know, RISC-V has a base architecture and then lots of extensions. RISC-V is designed to be very, very customizable. So not only their extensions maintained by the RISC-V International Organization, but there are also companies and academic institutions can say, wow, I want to invent 3 instructions, and you can go ahead and you have the full right to do so and put any instruction you want in the in your processor, right? In this case, we're talking about an extension, the RISC-V vector instruction, which is in the process of being ratified by RISC-V International in the version what's called 1.0. Right, so support for this RISC-V vector instruction. We support both the older 0.7 spec. Those of you that follow that, there was a fairly stable release of the spec called 0.7, and we support that one, but we also support the 1.0 specification. The 1.0 specification is substantially different from 0.7, and we do support LMOL, we do support segmented loads. We do not have the vector atomic extension support. So we have the full vector specification. And we believe we're ready for out-of-order support. So if you'll see in a second, if the team connecting their vector unit to our core wanted to do out-of-order execution, we believe we're ready for that. And it's probably requires a long discussion, but I'll be happy to do that. The way we've approached this is that Avispado, our core, executes the vector memory instructions. We'll discuss that. And then it connects to a third-party VPU. And in fact, that's what we've done in EPI, where the VPU has been done by the Barcelona Supercomputing Center, BSC, and Uni Zagreb together. So, the core talks to the VPU using this interface, which we call the Open Vector interface. Let me go into details about that. Here's how an Avispado 220 with a VPU would look like. The pipeline we've seen is the same I explained so far, so no major changes. Obviously, in the decoder, we decode the RISC-V ISA, and the decoder does quite a bit more, right? It does maintain state for 3 very important registers in the vector specification, 3 registers called V-type, standard element width and vector length. Those of you that know the vector specification know that these things can be changed with an instruction called vsetVL. So it is very common in vector programs that you do a loop, and at the beginning of the loop in assembly language, you say, okay, in this loop, I'm going to deal with whatever, 64 elements, or I'm going to deal with 17 elements, or I'm going to deal with 128 elements. That number is called a vector length, right? Associated with that number, there's the standard element width. That's the size of the data types you're going to be working on. So if your loop is working with floating point 32, SCW would be 4 bytes, right? If you're working with floating point 64, that would be 8 bytes, and so on and so forth. So it's very important for the decoder to know these things, because certain instructions are slightly different or are decoded in a slightly different way if the SCW changes, right? So we need to know that. Effectively, what I'm telling you is that when we see that the program changes any of these three things, we stop the decoder until we get that information back, and then we resume decoding. That way, for example, if vector length is 0, we can, if the vector length is 0, we don't need to issue any vector instruction. So that's an important change here. Then the other thing we do when we want to connect a third-party vector unit, like the one from the BSc, is we have this interface called the OVI, the Open Vector Interface. I have another slide going in a lot of detail over that. How does this work, right? Think of a vector load. Actually, here we have the vector load instructions as an example, right? If you, actually we have all of them. We have a vector load element, vector load strided element, and vector load XE index element. That's a normal load, a strided load, or a gather vector instruction. How do these work? Well, they go through the decoder. We at the decoder, we know, okay, we're working on this SCW. We know the vector length, maybe, I don't know, let's say 24. We want to load 24 elements from memory. We ship the vector load VLE instruction to the MIQ. The MIQ passes that to the VAGU, and the VAGU says, okay, what do I have to do? Okay, I want to load 24 elements, each one 8 bytes long, from this starting address. And the VAGU does the computation to say, okay, I'm going to break that down into cache lines. So if the first address is in the middle of a cache line, maybe there you find 3 elements. Okay, fine, you'll find 3 elements there. Load the first cache line, then we'll load 2 more cache lines, and maybe in the last cache line, you'll find a piece of data. So that's the job of the VAGU, to break down these instructions into cache line chunks, right? And to think in terms of cache line chunks and say, okay, I need 5 cache lines, I need 3, I need 4. If the programmer is nice and it gives us things that are cache line aligned and multiples of cache line, then everything is fantastic because the efficiency is maximum. However, many programmers, a lot of software is not capable of having all of its arrays fully aligned. So, okay, in that case, the vector AGU will deal with that on its own. More stuff on the vector AGU, the vector load strided instruction. What is that? That's an instruction, if you go to the specification, that says, I want to load 24 elements, but hey, each element is separated in memory by 950 bytes. That's the stride. So what the VAGU does is it will iterate on this and say, okay, where's the first element in address 100? Okay, where's the second element? Well, I'll add 950 to 100, I'll get to 1050, and that's where the second element is. And the VAGU will figure out if the different elements it's accessing, are they falling on the same cache line or are they falling in different cache lines? If they fall in different cache lines, obviously it will make 1 request per cache line. If they fall in the same cache line, it will optimize the request and say, oh, we've been lucky. 3 requests for this strided load happen to be on the same cache line. Let me only make 1 request, right? So then the VAGU sends the request down the memory pipeline. Now, once the VAGU really is has the job of taking these big instructions, a vector load wants, you know, in the EPI case, it can want even all the way to 256 things, right? And the vector AGU has the job of breaking it out into units that are consumable by the rest of the pipeline. So that's exactly what it does, and it sends the request. Now, at the same time, we need to coordinate with the receiver of this information. We're doing the loads. The loads go to memory, to this coherent interface, but when they return, we obviously want to give the data to the VPU, which is the place where we're going to use the data and where we're going to operate on the data. So what happens here? The OVI, and we'll describe that in the next slide, which is also a long slide, we coordinate through the OVI this delivery of data with the VPU such that when the data arrives, the VPU knows what's arriving. Okay, I got a packet of bits coming from the memory. Where should I put it? Which bits are good? Which bits are not good? Et cetera, et cetera, et cetera. I'll check the chat for a second in case there's a question. Happy to take a question here. Oh, there's Sanma entered the waiting room. I have to admit, I admitted someone. Okay. Okay, so that's one of the very important interfaces we'll describe. Obviously, the other part to connect to a third-party VPU is that when we see a vector add instruction going through the pipeline, through the decoder, obviously we have to send it to that VPU. So if we see a vector add, we decode the vector add, we say, okay, that's for the vector unit. We put it in the vector issue queue, send it through the OVI interface, and tell the VPU guys, hey, here's a vector add. Do whatever you have to do. Let me know when you're done, right? Questions? Okay, let's go to that interface in more detail then. Did I forget? Oh, there's something on the chat. Will the VPU use the data from the Dcache? Yes. So excellent question. Actually, I thank you for asking that question because I was going to forget a very important piece here. When a vector instruction is broken down into its individual components, into its individual requests, they'll go through the Dcache. If the data happens to be in the Dcache, we will happily send it to the VPU immediately. Now, if you talk to the HPC application people, they don't expect to find data in a little 32 kilobyte data cache, right? So if you talk to the HPC people, they're always thinking, well, that cache doesn't matter to us. However, what's a key part of your question is that in case the software, for whatever reason, correctly or incorrectly left something in this Dcache, we will find it. In that way, the loads and stores are fully coherent with the scalar loads and scalar stores. That's a lot of work for the hardware guys, but it's a blessing for the software people. If you worked on a non-coherent machine, you'll know how many bugs the software guys end up having because there was a cache line that was remaining in the Dcache and it didn't make it out of the cache, or the opposite, that you made a vector load and you thought it wouldn't be in the cache and then you find it in the cache and things like that. So yes, the vector loads, the component of the vloads will look the cache. Most normally or most commonly, the data will not be in the cache, no problem. Make a request to the memory system and come back. And however, if the data is there, we'll use it. Also within API, we have added bits to control allocation on this Dcache. So we can have the vector loads and stores say, okay, I'm okay that you look in the Dcache, but if the data is not there, don't put it there. Just give it to the VPU directly. Don't bother polluting the Dcache with this vector data. This is great for streaming. Great question. Thank you very much. Any other questions? Okay, so let's go into the details of the vector interface. Oh, another one. What is the maximum size of the VLAN in the data path? That's a choice by our customer, really, right? So we don't have anything in the Avispado side that's a limit. It's fundamentally a choice of, okay, how many lanes the customer is building the VPU and how many bits they decide for VLAN. So that's not really our choice. And I'm thinking, as I'm responding to you, to give time people to type another question, but I really think we are not determining, because the number of registers is fixed, and that we need to know, we meaning the Avispado side, and the VLAN doesn't really matter in the sense that we, the state machine in the VAGU needs to know the max, but that's about it. So if a customer comes and says, I want 16,000 bits, that's doable. Okay, going once, going twice. Okay, let's go into the, oh, I'm clicking the wrong place. Oh, okay, the open vector interface, synchronize the data. Yes, we've explained that. So we'll go into detail. So the OVI interface, it's actually public. You can go to GitHub and download it and read it. And if you want to use it, don't use this presentation. Go to the document. That's that's guaranteed to be up to date, whereas this presentation could be out of date, right? So anyway, let me describe a little bit. If we go back and you think about this OVI interface, these two set of signals, you have your own vector unit, possibly with secret instructions that you want to do. What do you need to implement to talk to the core, right? Well, the first thing that Avispado will do is send you this group of signals are the, hey, I'm sending you an instruction, and I'll go in more or less detail through this, right? Hey, I'm sending you an instruction. We give you the full 32 bits of the instruction. As you know, the vector instruction could have a scalar operand, so we give you the 64 bits that we read from our register file, and we give it to you, and so you can keep it there. SB stands for scoreboard. This is really a transaction ID, and we can configure this to 3 or 4 bits or more if needed, depending on how many outstanding instructions the VPU wants to have. So 3 bits, you could have 8 outstanding instructions and a valid bit, right? And the VPU gives us back an issue credit. So we assume that this thing is going to have a little queue, but you can build it without the queue. In any case, when you give us a credit, it means you're willing to take another instruction. You give us 5 credits, we'll give you 5 instructions. So it's up to you to manage this interface. I'm talking to you guys and assuming you would want to build your own VPU. So when I say you, I mean the company or the institution wanting to do this vector unit, right? So that's the first fundamental interface. All instructions that are vector are sent to the vector unit so they know what's going on and what happens. And they control the flow with this issue credit. Then there's also another set of important instructions because Avispado is a core with speculation. It could be that an instruction gets killed because we misspeculated the branch. So we have a way to tell you, oh, sorry, this instruction number 7, the scoreboard ID, sorry, we want to kill it, right? And you have to deal with that. And we also tell you, hey, this instruction is now the next senior. That means this instruction, again, identified by the scoreboard, this instruction is the one that's oldest in the pipeline. So you're guaranteed to know that that instruction will succeed. So that's another important information. In return, we get from the VPU all the completed information. That's very tedious. I will try to spare you from the pain of reading that. But basically, the VPU says, okay, I've completed instruction 7. Here are the floating flags, the saturation flag, a valid bit, the destination register. vstart is important. Those of you that know the details of the vector spec, vstart is important because it's if you have not fully completed the instruction, and that's legal in the spec. So you had to do 75 things and you only did 70 and there are 5 left, then vstart would be equal to 70, telling us, okay, the next time you give us this instruction, we don't want to start at 0, we want to start at 70. And there's also a retry bit. So we give the opportunity to the vector unit to say, you know, I got into trouble, something bad happened. Can you please resend me this instruction if you don't mind, kill everything and let's start over? So that's a possibility. It's not good for performance, but it's a possibility for the VPU. Then another very important signal that we need to synchronize is the VPU tells us when it's ready to receive data. So, you know, we send the VPU a vload, And it could be that the vector unit, for whatever reason, maybe for the internal arrangement of the register file, maybe because it's busy, there are many reasons. Maybe it's not ready to take the data from the vload. So then this memop sync start is a super important signal that says, the VPU says, okay, I'm ready to start the oldest load that you sent me. And when we receive that, then the load data path is activated and we start shipping to the VPU data. We send data at 512 bits per clock. We give the VPU a sequence ID. The sequence ID tells the VPU, okay, of all the vectors that you requested, this is element 17, a valid bit, a mask, and a mask valid. So the masking is another story. Also, we also, when the, I don't know when that's out of order, but after the load finishes, we finally send a syncan saying, okay, we're done with the load. This is the load that we finish. And in case something went wrong, we give them the vstart value. So that's the full protocol to interchange information. Stores work the same. Store, when we send the store, sync start, and then the VPU is the one sending the data to us and gives us also store credits. And we give them a store credit saying, oh, don't send me too much data because I'm having trouble. Maybe the CHI queues or the coherent interface queues are full, or there can be multiple reasons why these could be full. And also there's an interface for sending masks back and forth. The masks are a pretty complicated matter. All the vector loads and stores can be executed under mask. And so we need to communicate the mask information between the VPU, which is the owner of this mask information, back to the load store unit so it knows, oh, this load is masked, so don't do it. Don't take a fault on this load. Okay, we got 10 minutes left, and that's about it, what I had. So I'll pause here for questions. I'll show you the last slide while we wait for questions. So we basically described today the Avispado 220. It's a 2-wide in order with gazillion misses and supports the RISC-V vector specs 1.0. And in case anyone listening is interested, it can be available for listening, or maybe you're interested in working with us and helping develop this technology. We are hiring, so feel free to send us an email, send me an email, or get in touch with us. So thank you very much, and happy to take more questions.
Yeah, thank you, Roger. Thank you very much. Pretty interesting presentation, especially on new technology and RISC-V, and we all hope that RISC-V will have the success that it deserves, and so important for the overall plan of the European Union, as we heard before from Joe Wood. Is important for Europe to really become competitive, to be able to count on open hardware, not just on open software, and to be able to leverage the activity of entrepreneurial activity, small, medium-sized enterprise like yours. I think they're very, very important for the European ecosystem. So, question to Roger. I don't see any on the chat. Of course, if you are still thinking, and of course you will have access to the slides and to the recording, so you can then either through us or directly to Roger address further questions. And as Roger said, I mean, this school are also an excellent opportunity for those students who are already looking for a job, for an internship, or really for a permanent job, to be in touch with the lecturers, especially when they are from industry, like the case is for Roger Espasa. So there was a question, but I don't know if that has already been answered by Christian Ramirez. What is the maximum size of the?
Yes, no.
Yeah, but that has already. And then after that, thank you for your lecture. Thank you. So everybody is happy.
That's good.
I mean, your lecture was, very well done, nicely and articulated. So, of course, as you probably imagine, I heard of Avispado before, but no, I think it's fine. Okay, so, well, that